Hi. So, working on a problem and have done a little research and I'm about to build something. So, let me just explain the problem here. I'm using OpenStreetMap data and it has key value pairs tags that are on each set of point in this data. So, something might be tagged Starbucks, something might be tagged a street, so on and so forth. There's like 3,000 tags. Like, if I load up my data real quick. Well, that's not what I was expecting here. If I load up my data real quick, let's make this a little bigger. Let's do this. If I do select count star from entries, JSON each. Oh, I gotta remember how to do this. JSON SQLite JSON each. Even though you can use it every day, it doesn't mean you remember how to use it. Okay, JSON each. Okay, yeah, that's what I thought it was. Entries, tags, and then let's find distinct count of JSON each. So just returning a distinct list of tags, just the keys of those tags, right? So there's 3,300. That's a lot of tags. So what I was trying to figure out is there a subset of the tags that have high cardinality that when using that subset of tags provide the most value, most information value, right? Because some of these tags, maybe they're only used 3 times across something like 4 million different points. So I wanted to write a program to do that. Originally, I was going to do this in SQL, and then I started doing all the SQL, and I was like, I don't think this is going to be in SQL. So we're going to write some Go code. The problem that we're trying to cover is the set cover problem. And what this means is that you have a bunch of different sets, so the tags and the items that are tagged, and we're trying to figure out what combination of those tags, those sets, will give us a maximum number of items in that surface area. And then, there's a Venn diagram here and all that stuff, but I say let's start writing some code. I'm going to keep this open because that could be useful. I'll make this a little bigger. CD tags. I got a little project that I've kind of already started here. It doesn't do anything yet, but main.go, package main. Who's got the funk? Is. All right. First, we're going to need. Come on, dude. Go SQLite 3. Boom, 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 boom. Get this. So what we can do is import SQLite. We're gonna do database SQL. And then we're going to load up our SQL file. Error. I like this pattern better, so I'm just going to do this. Okay, so that way I can return an error rather than log fatal everywhere. So SQL, open. We're going to do SQLite 3, and we're going to do a file dash nowhere test db if error not equal to nil format could not open db for reasons. Okay, so what we want to do is get a list of all the tags and the IDs associated with those tags. So we're going to query for select each .key, and then SQLite doesn't have an array type, so we're going to have to do this in a cheaper way, which is the group concat, and we're going to say that entries ID separated by a comma from entries from, I can go back over here just to see what the syntax was. JSON each tags. It's good because I always forget. Entries, tags. Since we have a group concat, we need to group by something. So let's do JSON each.keys. And this returns rows. Error. Take this real quick. If error cannot, move this back just a little. It's a microphone right here. Read DB. Okay, so for our rows, we have 4 rows.next. So what we're going to do is tell you what, let's just print out this data. Let's just see what it looks like. So var IDs is a string, double string, key. So we row scan key. Oh, IDs, fancy error here. Cannot scan DB. For good practice, we should also do a defer row close. And let's just print out this information at the moment. What do we have? Just see if what we expect. Printf tag equals -s in IDs. Let's just make the length of the IDs because it's going to be a giant string otherwise. So key and then length ID. So if I run this by doing return nil, do go run main.go e.go. No such column key. That is correct. Take a moment. It's eating memory. Not eating that much memory at all. And they're in alphabetic order. Well, that's really nice of it. So yeah, it looks like some of these things are returning. So I know the data set I have is from Colorado. It's got about 4.2 million data points. So we are seeing things return large number of data points, large number of IDs, which is incorrect because that is the length of the string of IDs, not the actual. Yeah, that is not correct. So how about we just do this? I did not mean to do that. I am sorry. There we go. That will give us the right, not just the length of it, but the actual number of IDs. Oh boy. Okay. So yeah. Okay. Some of these IDs are a little better. So if I went up to, where was it before? Power. Yeah, those are looking a little better. 300 for one thing. Okay. Cool. So we have something that represents the tags and ID, right? So let's put this into corresponding sets. So tag set would be a map of the tag and then an array of string. And then we're just going to put those into tag set key equals IDs. Okay, so now using this algorithm right here, set cover, there's a greedy algorithm. And the reason why I'm saying greedy is that this is the cheapest thing to do. It's kind of brute force, but it's a good brute force. I don't know how to explain that any better. What I mean this is it's a brute force algorithm, but it's still an optimized brute force algorithm. So the idea behind this is that you're actually going through you're keeping track of all the items that could exist, and then basically going through each tag and then finding the one that gives you the highest cardinality by adding that tag. So what that means is the first step would go through this list that we have right here, find the one that has the max number of IDs, and then take that off. Then it would go through the list again, take the next one that provides the highest cardinality. And cardinality here is the number of items in that set. So if the previous set has a cardinality of 10, and then you add a tag and it gives you another cardinality of 10, the cardinality hasn't changed. So let's just brute force it. So I'm gonna kind of do this from what I think it needs to be implemented in. Maybe ChatGPT this up at some point. But I know what we need to do is get all ID. There's 4 million. So what we need to do is go through each list of ID. Oh, never mind. I'll just do this right. Nope. Hold on. We can do it right here still. But we need a set. We don't want just a giant list of things. So a set in, let's do this just so they line up perfectly. A set in Go is a map with a struct type at the end. So the struct type means an empty struct type just means there's no value that this map needs to return. And I believe Go actually under the hood will optimize this data structure so it will take up less memory. Not that I'm really concerned about memory here. And we're just gonna say IDs set ID, let's go on, and just an empty struct. So that way we should only get a clean list. Okay, so we got all the ID. So we want to keep track of, where's the list here? Okay, now this doesn't actually implement the greedy, but it does provide a good explanation of what we're trying to do. We're trying to find the locally optimal choice at each state. So find the max cardinality each time. So that means we have to go through the list each time. So that also means we have to keep track of we need to have a list of tags selected, right? Like what's our list of tags? And we need to keep track of, do we need to keep track of anything right now? We need to keep track of what tags are used in the cross section, right, with those selected. So if we're using 1 and 2 and 3, we know we're covering quite a bit. Okay, yeah. So used tags. No, used IDs. There we go. Used IDs. Cross. Is that a cross section? Yeah. Used. We'll just use used ID. And this is going to be another list of string. So what we're going to say here is where let's do a for loop. And what we're going to do with the for loop is say we want to go through each tag IDs, and then we want to do range tag set. And what we want to do is find the tag with the max added coverage. So if we there's going to be a lot of for loop. Sorry, I'm just thinking if there's another way to approach this in terms of we need to do unions. And Rails, I've been doing a lot of Rails, and Go doesn't have a good union type. It's literally just like we're going to have to do this explicitly, but we want the set. I'm starting to see a pattern here. Okay, so given our I don't like that. Covered IDs, maybe that's covered. So we want for ID. This is gonna be expensive. That's okay. Map struct. I got it. Struct ID. Okay. So we're keeping track of that one, and then we're gonna add. I got it. And then we're gonna add the current one of the tag set. So ID. So this is a union. I want to rename union IDs. How about union of? Okay. And then what we want to say is if the length of union IDs is greater than the length of covered ID, well, then we need to keep track of this tag, right? It's like max tag, sure, and max count. Do we care about count? I don't know if we do. So we just care about the max tag. So max tag equals this tag. So really what we're looking for is, it's not the max tag. It's the tag that returns a maximum number of items that covers this union. And I know I said union, but I meant, yeah, no, it's a union. Okay, so then we have it, and then we have a list of tags selected. We can append that to tag selected, max tag. And then we need to actually add these covered IDs. So we need to actually perform that union. So let's do ID, range, what am I looking for? Tag set, max tag. And we're just gonna add all those actually covered. This to beach makes perfect sense. Okay, so the result append is never used. Yes, so how do we get out of this? Oh, well, we have all the tags, right? Yeah, that's one way to do it. If we can say the length of covered IDs equals, continue this while the lengths are not equal. Yeah, and then I return nil because I need to return nil here. But then can I just print out the tags and the length just out of curiosity? Okay, so I don't want too much on here. I got rid of this. Might take a while. Well, let's see. I might have to add some print statements. Oh, that's using a gigabyte of memory. Well, it's not that much. And is it working? Seems like it's working. Well, I got no complaints. This potentially could be an infinite loop. Tell you what, why don't we take a little break while this processes? Here, I'll just put up my good old, I'll be right back. Well, it's still running. I think we have an infinite loop here. So I said to keep going while this is true, but really it is, if this ever reaches a case where it will never be true, it'll just keep for looping through this and potentially just adding an empty string to this max tag. We're not keeping track of, if there's no delta here, like if there's a possibility that we cover everything or there's just no more tags that can be added to the set, right? Like we may not cover all the tags, which this covers, but there may be a case where we never add any more tags. So I'm running out of names. Just previous count int. So if we find a max, so it's just going to be the len of union. It's more like I want to know if there's no change. So it's like the delta. So that way, if there is no change when we get out of this for loop, and delta still equals 0 because that's the initial value, it should always be something greater than 0, even if it's adding 1. If it isn't, let's get out of this. All right, let's see if that helps us. All right, we're gonna need a lot of memory. I think a lot of memory is coming from the fact that we're using strings everywhere here. I bet if we used integers, it would help out a lot. I think it would probably help out a lot here too, just with the copying of strings everywhere. It's using more memory. Might need to add some logging here to see where it's at. I don't know how much time is too much time. So this is interesting when using a brute force method. It's trying to find something optimal, can it? All right, 2.5 minutes. I'm gonna stop it there. Feels like it should be able to find something. Tell you what, for the sake of exposure, let's do it on a shorter amount of elements here. Let's do it on 100 elements instead of 3,000. Let's see if that helps us out with anything. Just to make sure it's not stuck in an infinite loop. Oh, yeah, I should add, what's called greedy. Well, we know if we're only doing it with 100 tags, shouldn't do this more than 100 times, right? So how about we do, we're just gonna do it will print out something eventually. Or maybe building these sets just take that long. Tell you what, let's also add here. I have a feeling it's taking too long, just because of this for loop and the number of unions added. It just gets really slow because of how many things this has to copy over and over again. Because the list, I mean, it's 4 million things, and if we just hit something that happened to be that, yeah. Okay, well, Golang map copy? Well, you have to brute force a copy. There's no command. Okay, so it might have just been taking this long. I thought they added that to Golang. But copy might just be for arrays. Clear was for maps and arrays. I see. It's funny, even with 100 tags, it hasn't hit the sweet spot yet. I kind of want to wait and see what happens. So, I mean, the issue is, okay, here we go. And there's 76 tags. So it found, okay, so it did. So it must have hit this thing. Eventually it found, out of those 100 tags that were returned, only 76 of them were needed to find. Hey, it worked. Oh, wow. So this is pretty slow. I have a feeling it's because we're using strings everywhere. I'd like to change this to actually use IDs. And I always keep this open because this is one of my favorite libraries in Go. So let's use this. I'm just gonna use it for the map. Here, actually, you know what? Never mind. Let's do range. Home on the range. Let's get the uint ID. Let's assume all the IDs are correct, and let's do strconv, parse uint, the ID string 10 and 0, and then we're gonna do append. And the reason I'm doing this one first is because this is gonna tell us every time I change a type what I need to fix. Okay, so this one's complaining about this. So if I do uint 64, now the type is like, I don't know what this is, and I need to change this one to be uint 64. Now I need to change this one to be uint 64, and then I need to change this one to be uint 64. Cool. So 76, and it took a while. Three minutes. All right. Well, that's already faster. It looks like just using int64. In the grand scheme, it's just less to copy around. Strings just take up more memory because they're taking up more space. It's already going fast. It'll get to 76, but it's going to take less than a minute, is my prediction. Oh, interesting. 79? Is that where we went before? That was 76. And this is still just over a list of 100 tags. Can you imagine doing this over 3,000 of them? I'm surprised it's not the same number of tags. But is it the same tag? Four-wheel drive? Well, here's another thing just to help with that. Let's sort our tags so we can see them more often. But I do see 76 is a big cross-section, and we can't just do this for 100 of them. So, what do we do? There are two approaches I can think. Just let it brute force and just come back in half an hour to an hour, or use a different data structure. I'm leading this. So, we have a set of numbers that we need to be able to iterate over and then do operations over it, like these unions. I just happen to know that things like bloom filters are really good for well, sorry, not bloom filters, but the underlying data structure of a bloom filter, which is a bit, right? You can keep track of numbers, just that a bit is turned on in some sort of place that represents that number in bits. We have what, 4 million items, so we have 4 million bits, and if one of them's turned on, we know that bit is in that set. The problem is that we know that not every 4 million items is in every set, right? We're looking for that cross. So there happens to be something called a roaring bitmap, which is a bit set. Bit set? Am I using that right? Yeah. No. A bitmap. Sorry. A bitmap, which is a bit set is a bitmap, or a bitmap is a bit set. I don't know. Here, let's say, is a bitmap a bit set? Bit sets are also called bitmaps. Okay, I'm using that right. Okay, great. I was just confused. Okay, so a roaring bitmap is a compressed bit set. So the idea is that you can give it just a bunch of numbers, a giant list of them, and it will just be like, oh, okay, like I'll compress this so they're easier to access, representing the set of numbers that you gave me, and use some, I'm using hand wavy because I don't understand how it compresses, some compression underneath. So it can help you put 4 million items into a set. But the nice thing about bit sets is if they're organized well under the hood, doing operations across like unions and stuff like that is using bitwise operations usually. And those are faster than anything I could write here. I mean, I could write my own bitwise set operations here, but I don't want to. So, tell you what, we're going to take this thing and go get it. We're going to get the roaring here. And instead of keeping track of an array of uints right here, we're going to do an array of roaring bitmaps. And now this is going to just complain about that operation. What we can do is just do a roaring bitmap of this. It doesn't like that. uint64 instead of uint32. Yes, we need uint64 because we know that the IDs of OSM can be int64. So uint64 is just good to use. But this uses uint32. uint64? I don't see anything. Roaring 64. Hey, they already got us covered. Look at that. So if I just do this, I'm just going to call this roaring again. I'm assuming it has the same interface. Hey, look at that. Okay, so there's going to be some of the reds here. So our ID set could also just be a roaring bitmap, where we could just say this is a roaring bitmap new. And then how do we do a union here? Union? We need fast functions to compute unions. Yes, I agree. How do we do unions? Computes union of the 3 bitmaps in parallel. So an OR operation. I'm guessing this means parallel. I don't really care about parallel. So can I just do IDs set.or.tag set dash key? Cool. So that gives us all of them. So we're gonna make this another roaring .new. And so this becomes roaring.new, and it gets OR. Can it do that? Can it do an OR here? Yes. Covered ID, and then a union, and then we can just do another OR with these IDs, and these IDs. Just do that. Nope. ID. Okay. We don't have that length here. What do we have? Length. Union dot length size. Ooh, cardinality. Cardinality? Get cardinality. And what does that do? Cardinality returns the number of integers contained in the bitmap. Beautiful. Why don't they just call it length? And then I'm just gonna copy this here. -1. Oh, it does not like that because this is uint64. That's all right. And then this down here. And then we can just do covered IDs or tag set max tag nor red. So now we're just using these compressed bitmaps to handle the representations of a holy moly of a set for us, and that got us to 75. So is that consistent? Is this just difference in implementations that we get different tags, or is it the order of which the results are being returned from in 76? Okay, so I think there's something with the order of tags being returned. Maps in Go are non-deterministic in terms of how when you iterate over them, the keys. So that would explain why we get 75, 76, 79 around that error. Okay, I mean that's not that bad, but incredibly faster. I wonder if I add my original. I'm gonna keep the count in there, but I'm gonna get rid of this. And can I say when covered IDs equals all ID set. So as long as it doesn't equal. Okay, so let's run this now just with 100. And so we should get 75 again, but it should exit on its own now. Exit on its own. 72. Now let's run it one more time. I'm seeing something interesting with the tag names here. You know, some of these are uppercase, some of them are colon. All right, 75. Okay, so my hope is if I get rid of this, do this. Let's see how much memory is being used now. Running bitmaps. We're using a gig, right, with the string. I mean, kind of see it getting slower, but it's still faster than it was with 100 items in string. And it's only using 77. I'm rounding up. What kind of CPU is this using? 200%. So that's not that bad. Remember, there's something like 3,000 tags. Is the right combination a very large set of tags or a very small set? The fact that we're already at 300. What I should do is probably also spit out the number, the total number here, and the number already collected. So as I say that, I'm going to do that, just so we have some better output. Total is going to be get cardinality, and then this you went C4, so I can actually just use that. And I'll just do current, which would be current ID. Yeah, that sounds like a better name. I wish I had some math to show how well this works. Like, I mean, this is brute forcing it. I'm just gonna let this run for a minute. It's still running. It still looks speedy between each set. It's taking half a second for each iteration. I'll just come back in a moment and find out. I'm gonna put the BRB so you can skip through this. So this is still running. So what I'm worried about is that I haven't stopped it, and I don't know what the current count comparison of how many tags it actually has. What I'm worried about is that the cardinality of some of these tags might actually be just 1-to-1, where it might be this single tag represents this single thing and nothing else. It would be bad. So I want to go through this real quick just to see if the logic makes sense. We're finding all the IDs for a specific key. We do a group by. I'll just fix that real quick. We then go through each tag. And then we say, here's the list of IDs as uints. We keep track of all the tags, all the IDs, sorry, that come in. We then start with an empty list, an empty set of tags, IDs. And then what we say is go through each tag. So potentially the issue I can also see right here is we're not subtracting away from this tag set when we're done with it, meaning once we've used the tag from this tag set, we don't delete it because we don't need it anymore. Otherwise, we're just doing this operation over and over again for a bunch of tags that it already knows about, and this would have. So that's an optimization we could do there. It would make it go a little faster. I'm gonna stop this. Let's see. So that's been going for quite a while now. I'm also wondering if I need to figure out if there are tags I just need to get rid of because they're not valuable tags. That's not what I was expecting right there. It does increase each time, but I'm pretty sure that's not the max value, considering... Here, I'll stop this for a second. Considering that this jumped 3,500 points, why didn't it not find... Sorry, 35... A count of 3,500... A count of over 6,000, there we go. But it didn't find that in here. Oh, was the cardinality higher compared to previous things that ran in this? No, this is just running through each thing. Stupid. So we need to keep track. We keep track of the delta. And what we need to do is, if this new delta is greater than the old delta, we weren't comparing it to previous things in the list. I bet this is going to go so much faster now. Hey, look at that. So many more things in the list already. So it's finding the max value. And it's getting there. It's just finding smaller subsets each time. But out of how many tags, what was it, 3,300 tags? It's got almost 40. Come on, little guy. From dress. So close. It's only like 100 at a time now. See, it's getting really, so now we're at 60 tags. But it's working, right? Like, that's the incredible thing. It's doing the thing that we wanted it to do. Yeah, now it's getting to tags that have such low cardinality that it's just skipping 20. So it's going to take a while for it to get to 700 here. That's pretty cool. And since we delete the tag, we know it's actually not trying to recycle a tag already. Okay, we just got to see what this looks like. So this is going to take a minute or so. So what we've learned here today is doing something brute force and still continuing it to do brute force, but adding better underlying data structures has sped this up for us considerably. We went from not being able to do anything with strings then cutting it down to just a subset of those tags to see what was slow. We switched it from strings, which was using a gigabyte of memory, to uints, which was using 70 megabytes of memory, and then switched it over. Then we had something that we felt comfortable with after running it a few times. Switched it over to roaring bitmaps that uses bitmap/bit sets to compressed sets of uints, and has operations on it that use bitwise operations that make our set operations go so much faster than using maps. And then I turned it on to use all the tags, and we're not even hitting 70 megabytes of loading 3,300 tags of all those integers. It's so close. Now it's just nitpicking at 2. How useful are those tags then? There may be something here where I have to filter out tags below a certain count, right? What's my threshold? If a tag only represents 1 or 2, if a tag only represents 1 or 2 items, is it actually that useful? Someone would have to know that specific value for that tag out of 4 million items. And is the uniqueness of that thing valuable? I would argue no. So for the sake of having something here, it's so close. Let's just doing one at a time now, so we know we got 27 more seconds. Let's say, what's my threshold? 10, 100, 1,000? Like, is something out of 4 million objects? Like, so 100 out of 4. I mean, we're not even talking close to a percent. So what would be a percent here? 4 million. Had to cover 40,000 things. So let's do 0.5%, or a 1/10 of a percent to have it be useful. Okay, there you go. That's our list of 226 things. And I bet there's tags in here that I could probably filter out that are not actually useful because they don't represent a value that would be like fix me. I don't know what paramiti is. But let's try this with the 4,000 real quick, just to see what it provides. I bet it would be so much faster because it's actually just eliminating some items that you wouldn't be able to tag. Yes, I have to, since I'm returning the value. I could probably update the SQL to not have to use this, but just for the sake of being here for a moment. So what do we have? 226 tags. Right. And what do we have now? 90. And we could still probably filter some of that. All right. I'm happy with that. These are high cardinality tags that provide value because they return a greater subset of things rather than just small subsets of things. And this is probably a value I could probably mess with a little to figure out, like, maybe there are 100 unique things. Like, I don't know, maybe there's like 100 Dunkin' Donuts and there's a tag for that for some reason, not just a name tag. Cool. Thanks for following me on this optimization adventure. I'm going to see what I can do with this data now that I have it. Have a great night. What's the old like and subscribe? All right. Thanks.